This is a brief introduction to trees, also called spanning trees, in graph theory. A tree is a connected graph that contains no circuits. So for the 5 different graphs here, we're going to look and examine the graphs and find out which ones are trees and which are not. So for example, for graph number 1, you can see that this is indeed a connected graph. All of these vertices are connected to all of the others in some way, shape, or form. And there are no circuits. There is no way for me to go around and come back to where I started without retracing my steps in one way or another. So this graph here is indeed a tree. Moving on to graph number 2, it looks like things are fine in that I don't have any circuits, but this graph is actually not connected. This piece that kind of moves from the upper left to the lower right is not in any way connected to the piece moving from the lower left to the upper right. Notice that here in the center, there is no vertex, okay? And so that does not mean that there is a point there unless there is a specific vertex drawn in. And so this graph here is not a tree. Looking at graph number 3, it's pretty quick and easy to see that this graph does have a circuit. There is a way we can traverse around and get back to where we started. And so graph 3 is not a tree. For graph number 4, this graph here actually is not connected. This piece that I'm tracing is separate from this one. And we also have a circuit on this part of the graph right here. And so this one fails on both aspects of being a tree. So that one is not a tree. And then last but not least, if we look at this graph, we can go from every vertex to every other, but we can't get back to where we started without retracing. And it is indeed a connected graph. And so this graph number 5 is a tree. Now, a spanning tree, or again, a tree, so those terms are used interchangeably, and I wanted to be sure I used both throughout this. So you'll see the same basic definition. It is a connected graph using all the vertices in which there are no circuits. And so there is a graph here, 3 copies in fact. What we're going to do is find 3 non-isomorphic spanning trees for this graph. So by non-isomorphic, again, we're going to look for trees that are not the same structurally from one to another. Okay, so with the first graph, one of the ways that we might find a spanning tree is to connect these 2 vertices here on the left and then go across, go up, and then go to the middle. Okay, so that is one possible spanning tree. All the vertices have been used and there are no circuits. Now, one of the things that again will be important to note is that structurally, if I was to take that spanning tree and just kind of unfold it, it would look like this right there. It would just look like one big line. So if you can imagine, again, taking this part and kind of unfolding it and laying it down, laying this side down, it turns out to be just one long line. So as we look for other spanning trees, we want to make sure that structurally they are different from this one that's right here, because again, we're looking for non-isomorphic spanning trees. So another spanning tree that I could find might start here in the middle and then work outward to each of the other 4 vertices. And so obviously that is not isomorphic. It is not structurally the same because in this case, right here in the center, we have a vertex with degree 4 in our tree. And here we don't have any vertices with degree 4. We have degree 1 on the ends and 2 for the 3 vertices in the middle. So that would be a second possible spanning tree. And then if we could come up with another one, it might look something like this. Maybe we start here in the upper corner and we go out to one side. Maybe we go to that middle vertex and then we go down. So one of the things that you might notice is that this vertex here in the upper corner in our tree has degree 3. We don't have any degree 3 in any of our other trees that we have made. And so as long as we maintain that vertex there with degree 3, we can hook this vertex into our tree by connecting to any of these other vertices. We can take a pick. It doesn't make, again, any difference. I'm going to connect this one right here. And so those are 3 non-isomorphic spanning trees for the very same graph. Again, to be a tree or a spanning tree, those terms are used interchangeably. It has to be a connected graph. All vertices are linked in, and there are no circuits.